Okay, so hello and welcome back. So in this video we want to start another chapter of this book, which is about diodes. So we are going to learn a couple of things about diodes, and I want to get rid of this multimedia here. Okay. So to start with, basically a diode is an example of a semiconductor electronic semiconductor device or component. As basically in this category we have diodes, we have transistors. We have transistors. There is different types of transistors. There is JFET transistors. There is junction field effect transistors. There is the ordinary type of transistors, and so on and so forth. There is a couple of things over here. You have Zener Diodes, which you can say it's some type of diode, but it's a little bit different. There is triacs. There is if I'm writing this right, triac electronics. So triacs. We have triacs, you have, I don't know, thyristors, you have, and I suppose a couple more things, even a lot more things, and a couple more things that I don't even know anything about, because they keep making new stuff out of semiconductors. Over and over again. So basically semiconductor is basically some material. It's basically some sort of material that you get out of sand. So sand is basically something that you can find in the desert, and there is enough of it on earth, I suppose. So you get this sand and you purify it. So you get the sand and you purify it and purify it and purify it, and then from that sand they get something called silicon. Of course, this is in no way a scientific explanation of this whole process. I might get a couple of things over here that might not be scientifically right, but that's kind of the whole process of getting semiconductors. And so then we have silicons, and then out of these silicons you have there is some process that we can make semiconductors. Now these semiconductors, what they do is that, for example, in the case of a diode, so the diode would be something like this. So you have a semiconductor over here. So this semiconductor, or a transistor, or anything else for that matter, a semiconductor, what it does is that with a semiconductor you can control the flow of electric current, meaning that under certain circumstances it basically does not allow the flow of electric current. For example, if you have a diode, for example, something like this, if you have a diode something like this. Now if there is basically, if you connect the power supply to this diode in this orientation, if you connect the power supply to this diode in this orientation, in diodes there is two leads. This is called the cathode, and this is called the anode. Now if you connect the anode to the positive pole of your power supply, and basically your negative, and the cathode to the negative pole of your power supply, there will be current flowing in this circuit. Okay. Now if you reverse the polarity of your power supply, meaning that if you connect your positive to the cathode and if you connect your negative to the anode, then there will be no current. Flowing through the circuit. No current will be flowing through the circuit, meaning that in one orientation it basically blocks the flow of electric current. In the reverse orientation, it does allow the flow of electric current. Now there is one more thing that is called the Zener Diode. There is one more thing that is called the Zener Diode, and that is usually the schematic for a Zener Diode is basically something like this, if I'm not mistaken, something like this, or the other way around, something like that. And then in a Zener Diode, basically if you connect your basically, now this is quite the opposite of what we did over here. If you connect your the positive pole of the positive terminal of the power supply to the anode, and the negative pole of the power supply to the cathode, no current will flow in this circuit. Okay. And of course, the way that these semiconductors behave, that basically does directly depend on how they have been made. They have been basically on purpose. They have been made in such a way that they behave in this exact way, basically, meaning that they have done all of this on purpose. They have made this so that it behaves this way. And so now in this Zener Diode, what happens is that if you connected the anode to the positive pole of your power supply, no current is flowing in this circuit. On the other hand, if you reverse the polarity of your power supply, connect your negative to the anode and positive to the cathode, then basically up to some voltage no current is flowing through your circuit. But then once you reach that voltage threshold, then the current starts flowing through your circuit, meaning that, for example, Zener diodes have voltage ratings, and of course power ratings as well, but the power rating is not that really important. That is just indicative of how much current can go through your Zener diode. Otherwise it's not that important. The power rating is also there in the case of normal diodes as well. But mainly these Zener diodes have some voltage rating, for example 5.1 volts. So the Zener diode is rated as 5.1 volts. That means that if you connect the positive pole of your power supply to the cathode and negative pole of your power supply to the anode, and if you have a variable power supply basically like this, just a bench power supply unit that you would normally have on an electronics bench, for example, you can you can start at 0 volts and then you can go all the way up to, for example, you can increase your voltage using some knob. You can just keep turning that knob and your voltage will be increased to, you can increase your voltage all the way up to even 20 volts, 30 volts, 40 volts, 50 volts, even up to 60. It depends on how the power supply has been made. But you can keep increasing your voltage, the output voltage of your power supply. Now if you do so, now suppose that you have power supply over here, a variable power supply, and the voltage can be changed and increased and decreased and so on and so forth. If you start with 0 volts, no current is flowing in this circuit, and you just keep increasing your voltage, increasing until you up to the point where you reach basically 5.1 volts. Of course, it's not that accurate. Sometimes it turns on at for example 5 volts, sometimes 4.9 volts, sometimes 4.8 volts, and so on and so forth. Sometimes 5.2 volts, 5.3 volts. There is some tolerance always there, meaning that the voltage rating is not always accurate. There is always probably even 5-10% tolerance there. But then as soon as you reach 5.1 volts on your power supply, then the current starts flowing, starts rushing through your circuit, meaning that if you do a graph of voltage, for example, versus current in your circuit, the current is 1, 2, 3, I'm sorry, the voltage is 1, 2, 3, 4, 5 over here, and then this is your current, right? So you can just, your current, basically your graph would be just something like this. It just keeps going, and suppose that this is 5.1 volts, for example, and we're talking about the 5.1 volt Zener diode. So then the current, the graph of the voltage versus current of this Zener diode would be this line, and then it shoots up like this. All of a sudden current basically keeps shooting up with a very high slope. Of course, this is just this is a perfect, for example, Zener diode, but in reality it might be something like, for example, something like this. Okay. So that's basically how a Zener diode works. So again, you are controlling the flow of electric current using this semiconductor. Now in the case of for example, in the case of a transistor, what a transistor is basically, it's again a semiconductor, right? So what it does is that again it controls the flow of electric current through the basically most of the time through the collector emitter junction of the transistor. On a transistor you have, for example, a base, you have a collector, and you have an emitter lead. So depending on the voltage, or basically the signal or the voltage coming into the base, then there will be some current passing through your collector emitter junction here, meaning that if you basically ground this lead over here connected to the ground, and suppose that you have some power supply over here, and there is a lamp over here. If you connect this lamp to this collector, and basically then ground the negative pole of your power supply, and connect the positive the positive of the power supply to the lamp, then the lamp will be turned on if you turn your transistor on. So once you turn your transistor on, current will be flowing through this junction. So from this side your lamp is connected to the ground or the negative pole of your power supply, and I'm sorry, from this side the lamp is connected to the positive pole of your power supply, and from this side the lamp is connected to the negative pole of your power supply, because these are electrically common. And then your lamp will turn on, provided that the transistor you turn it on, depending, and then that depends on what you do in your base. If you do a certain specific thing, in the case of a transistor, the transistor is turned on, the current starts flowing, and then you can basically do all kinds of things with this transistor. And the beauty of this whole process is that you can keep basically controlling this dynamically from second to second, meaning that this is not just like a switch that you just basically either turn it off or turn it on. You can actually, depending on what you do in your base here, for example, you can actually create some sort of mysterious resistance in between your collector and resistor, and with that resistance you would be controlling current going through this resistor, because you know that if voltage is constant, then if you change your resistance, your current will change. Of course, the higher your resistance, the lower is your current. The lower is your resistance, the higher is your current. And if you keep playing with your resistance here, the current going through that junction is going to change. And then you can do this dynamically from moment to moment. Now suppose that, for example, you do this, you connect this to some microphone. Suppose that this is a microphone. You connect this to some microphone, and some signal is coming from your microphone to the base. Now, depending on the signal coming in from the microphone, this transistor keeps basically turning on and off really fast, really fast. And then based on that, you can control the current going through this collector emitter junction, and then you can just simply connect this part, and then you can simply connect this part over here to a speaker, connected to a speaker. And then depending on the input sound that you speak into the microphone, there is some output sound at the speaker, and that's how a sound amplifier works. Sound amplifier basically works based on the principle that, based on the sound waves that you speak into the microphone, this transistor is controlling the current going into this speaker, and this speaker is just a diaphragm, in most cases, back in old days, it was just a paper diaphragm going back and forth, and that created some sort of sound waves in conjunction with the air in the vicinity of the speaker, and of course then that air hits your eardrums, and then you will hear some sound, for example. Now what this amplifier does is that it does, of course, amplify the sound coming in. It does amplify it, but it's a very beautiful dynamic process, meaning that depending on the signal that comes in from the microphone, the signal that is going into the speaker is being dynamically controlled. And that's the beauty of this system, and that's the beauty of transistors. Okay, so these are basically semiconductors in this was an overview of semiconductors in general. Now semiconductors start usually with diodes, and then you can just keep going and going and going, and you could not really get to the end of it because there is always something new in the world of electronics, and there is always something new in the world of physics. There is always something new so that you will never get to the end of it. But there is some basic things that you need to know about these, meaning that you need to understand diodes, you need to understand the Zener diodes, probably thyristors, triacs, transistors, and that's all about it. And then using these components, you can basically based on these electronics components and their characteristics, you can design your circuits. Okay, so now let's get started with the diode. Let's see how a diode works, how it's been made, and how we can use it in our circuits. Okay, so now coming back to the normal ordinary diode, basically the main thing that the diode does, and I suppose the only thing that the diode really does, as far as I know, is that it conducts electricity in one direction and it doesn't conduct electricity in the other direction. Meaning that, for example, first of all, a diode is usually something like a resistor. Is basically something like it's a cylindrical thing like this, and it has two leads. So you have basically this lead over here and this lead coming out of the diode, and these two leads are connected to your circuit. And of course you have to solder the leads to your circuit, that you might already know. Now, whenever you have a diode, basically what happens is that there is a band over here, and well, as opposed to this band over here, there is this is a printed band over here, and as opposed to this printed band, there is nothing on the other side. This lead that is on the left side next to this band is called the cathode of the diode, and this lead over here is called the anode of the diode. Now, basically what happens is that in very simple words, the cathode and then this diode in the exact same orientation, basically the schematic of a diode in the exact same orientation would be basically something like this. Do this properly. Would be basically something like this, like a triangle, and then this band over here is also there, and then you have basically, again, this is your cathode and this is your anode. Now, this diode, if I connect it to, basically, if I connect the cathode to a power supply, but to the negative pole of your power supply, and then if I connect the anode to the positive pole of the power supply, then it will conduct. It will conduct the electricity, or current starts to basically circulate around your circuit. And so in this orientation, the diode is conducting. And in this orientation, technically we say that the diode is forward biased. When the diode is forward biased, it's conducting electricity. And that's basically what it does. Now, in the exact same diode, let's suppose that you have the exact same diode, and then you connect it to a power supply, but this time I connect the cathode to the positive pole of the power supply, and the anode to the negative pole of this is positive, this is negative, this is positive, this is negative. So now this time I connected the anode to the negative side of the power supply and the cathode to the positive side of the power supply. And in this orientation, basically what happens is that basically there is no current going around your circuit. Current over here, there is no current basically going through your circuit because the diode is not conducting. And in this orientation, we technically say that the diode is reverse-biased. So when your diode is reverse-biased, it's not conducting electricity, and reverse-biased means exactly this. Your cathode is connected to the positive pole of your power supply. Your anode is connected to the negative pole of the power supply. And when your diode is forward-biased, it is conducting, and forward-biased means that basically the cathode is connected to the negative and the anode is connected to the positive. And that's basically all that the diode does. Now, of course, this characteristic of a diode is used in many different ways, in many different techniques, as parts of many different techniques in order to design electronic circuits. That's basically the whole story. Now before there were and one of the applications of a diode is basically the diode is used as a rectifier. This is one of the applications of a diode is that the diode is used as a rectifier. So what a rectifier is that basically whenever in nature everything, not everything, but when it comes to electricity is basically always naturally in the form of sine waves, something like this. Of course, this is not the best sine wave I've ever drawn, but naturally in nature, electricity is in the form of sine waves. I don't really know why that is, and I need to read a little bit of physics of basically electromagnetism and of course this is in turn also related to atoms and electrons and the whole nucleus of the atom and the protons and the and so on, the whole thing. But basically what happens is that electricity or current in nature is always alternating current, or AC, meaning that the current is basically half of the time positive, half of the time negative, half of the time positive, half of the time negative, and so on and so forth. So this is, for example, the AC power outlet in your home that you connect your laptop to this power outlet, you connect your lamp to this power outlet, and then you use it for different applications. But for whatever reason, or I would say for many reasons, we also need DC current, or basically direct current. We also need direct current. This is alternating current and this is direct current. The way that we convert AC to DC is through something called a rectifier, meaning that you rectify it. When you rectify AC, you will get DC. And a rectifier is basically four of these diodes basically put together in the form of something called a bridge. a bridge, they call it a bridge rectifier. Bridge rectifier. So what a bridge rectifier does, you have this diode over here. Okay, so you have one diode over here in this, let's say in this orientation, and then you have another diode over here connected to this, for example in this orientation, and then you connect this in, this has to be a bridge, meaning that the four ends of this bridge have to be connected into basically four diodes. So then you have another diode like this in this orientation over here, and then you have another diode over here in this orientation, and these are connected together in this manner. You can see that these two diodes, basically when it comes to these two diodes, the cathode is on the same side, and with these two diodes the cathodes are on the same side, meaning that the cathodes, for example, here are both towards the bottom of the page, and over here the cathodes are both towards the left side of the page. And then wherever you have two cathodes, this becomes the positive point of your bridge, and basically diagonally opposite to that point is the negative side of your bridge, which is basically two anodes connected together. And then wherever you have a cathode connected to an anode, that is basically called, that is where your AC comes in. And basically on the other side of the bridge over here, that is also again AC. So what this does is that you give your AC to these 2 points, this point and this point, and from these 2 points you will get DC. And DC is basically, compared to this current, DC is basically something like this. So for example, this is time, this is voltage, and a DC voltage or DC current would be just a horizontal line. It doesn't keep basically going up and down. It's not a sinusoidal wave. It's actually the same sinusoidal wave, but through some techniques, a part of which is the bridge rectifier, and we also use some capacitors. You basically connect the capacitor between these 2 points. We will get to that in the last chapter of this book. The same sinusoidal wave, suppose that you get this, you take this sinusoidal wave with your hand, and you just keep pulling it and pulling and pulling and pulling until it becomes a completely straight line, horizontal and parallel to the t-axis, or parallel to the horizontal axis. And of course a DC voltage can be a positive voltage. If it's above the horizontal axis, it's a positive voltage. If it's below the horizontal axis, it's a negative voltage. But it doesn't keep oscillating anymore. It's just a straight horizontal line. So that's basically, and then this is basically what your laptop, for example, can use in order to do different things. Meaning that on the input of your laptop you have AC voltage that goes into your power supply unit, or they call it the power bridge. They call it the power bridge. So the power bridge, what it does is that it takes the AC from the wall, and it gives you this voltage on the right, which is DC. That DC is plugged into your laptop, and then your laptop or your cell phone or whatever it is that you want to run on electricity, your laptop can understand this kind of information, not this kind of information. It doesn't understand. It couldn't work with that. So now long story short, for this kind of purpose, we need a rectifier. And a rectifier is nowadays always done with a bunch of diodes. For example, you could use 2 diodes, or you could use 4 diodes. You could even use 1 diode to rectify. But then there is all of these terms, like, for example, full bridge rectifier, half bridge rectifier, and things like that. This is, for example, a full bridge rectifier. And of course, full bridge rectifiers are more efficient than half bridge rectifiers. In half bridge rectifiers, you basically you will not get 1/2 of the voltage. 1/2 of the voltage is basically lost during a half cycle over here, something like that. I don't really know what I'm talking about here, because I've never actually done this myself. We will get to this. Once we get to this, we will talk more about that. But in a half bridge rectifier, it's kind of like half of the cycle. Every half of the cycle, you lose the voltage. The voltage goes down to 0, and then again jumps up to basically this point. Again, it goes back to 0, jumps up, and so on and so forth. So I suppose what they do, when they use a half bridge rectifier, they kind of compensate that with the capacitor, but that's not important for here and now. The only thing that you need to know for now is that the bridge rectifier is what we use in order to basically convert AC to DC, and of course, before there were semiconductors. Before there were semiconductors, transistors, and that sort of thing, there were vacuum tubes. And vacuum tubes were this big thing. Vacuum tube picture or image. Oh, sorry, I need to. Okay, so vacuum tubes were these big things. These are, of course, if you want to the exact dimensions of this, for example, this vacuum tube, it's, for example, this one over here, made in Russia, for example, as you can see. So these are the leads of your, or the pins of your vacuum tube, and then you have the plate voltage here, and you have the whole thing. It's just like a filament, like basically a filament lamp. There is actually a filament in there. That filament has to heat up, and then it's basically all about electrons shooting, and then there is this kind of something called a grate in there. There is something called a something that kind of blocks the electrons, and so on and so forth. And using the whole mechanism there, you can kind of have some control over the flow of electrons. You can kind of control it. And this was, of course, this was a big thing in its own time. Using these vacuum tubes, we made amplifiers, sound amplifiers, we made radios, and we made everything. Everything that needed, everything in which the current needed to be controlled, basically was back in 1940s, 1950s, and in those days, basically everything was made with vacuum tubes. And of course, back then, power was not that big a problem. Now, if you want to run one of these tubes on today, it would need a big chunky power supply, a transformer, and the whole thing. It would cost you, basically, if you run, for example, a small sound amplifier with tubes, and if you do it basically, I don't know, probably 5-6 hours every day, that would cost you probably around $500 every month worth of basically your electric bill or something. And of course, it's not, nobody does that anymore, that sort of thing. And these are, well, these are basically big. For example, the height of this thing might be even all the way up to probably 10 centimeters or so, probably something around 3-4 inches or so. So that's basically vacuum tube, and these were used as rectifiers back then. And then once we made semiconductors, then of course we stopped using vacuum tubes, and then instead of that we started using diodes. Okay, now a semiconductor, as some sort of definition here in the book, it says that the semiconductor is a crystalline material that, depending on the conditions, can act as a conductor, meaning allowing the flow of electric current, or an insulator, meaning preventing the flow of electric current. And techniques have been developed to customize the electrical properties of adjacent regions of a semiconductor crystals, which allow the manufacture of small diodes as well as transistors and integrated circuits. Now, to understand basically how a diode is made and basically how it functions, now I need to give you some information from the book. I don't have basically that much of understanding, at least from the memory, about the diode. But basically diodes are usually are basically made of two things. First of all, from silicon, and second of all from germanium. And of course you have hopefully learned enough about silicon or germanium in your chemistry courses. I have not done that yet. I need to go back and do this. So silicon and germanium, their atoms of course are different, and what I remember about silicon and germanium was that back then, like for example, I don't know, about 40 years ago or 50 years ago, of course back then I wasn't there yet, but I have seen many circuits or many electronic devices from back then, like 40-50 years ago. And back then everything was made with the transistors, the diodes and everything were made of germanium. For example, there was this transistor called, with the number AC, for example, 128. This was a germanium transistor. I can show you the packaging of the transistor as well. AC 128 transistor. See, this was, for example, the transistor. It's still available and it costs, for example, €4. This was AC 128, and this was from Toshiba, and you usually, for example, found this in audio systems. So this was usually used in audio systems, in radios and things like that. So these were germanium transistors. After germanium transistors, there came the silicon transistors. Silicon transistors were much more energy efficient and well, as far as the size is concerned, basically they were much smaller than germanium transistors in overall, basically. Now, today, there are still some applications in which you have to use germanium. For example, in some applications in radios, there are some diodes that still have to be made with germanium, but mainly germanium is not used in order to basically make transistors and basically semiconductors in general. So that's all about silicon and germanium. So here it says that silicon and germanium are semiconductor materials used in the manufacture of diodes, transistors, and integrated circuits. Semiconductor material is refined to an extreme level of purity, and then minute controlled amounts of specific impurity are added, which is called basically which is a process called the process of doping. So what they do is that they refine they refine these semiconductors. They refine them and refine and to a very high level, and then in order to basically control the behavior of those semiconductors, the semiconductor in the factory goes through some process called the process of doping, meaning that some controlled amounts of impurity is added to certain regions of the semiconductor, and then depending on the doping material and depending on how much of that doping material has been used, then the semiconductor basically behaves in certain ways, which is of course which is predictable because we have control over the process of doping. And now based on basically which impurity is added to a region of a semiconductor crystal, that region is said to be either said to be either N-type, or P-type. So that region of the semiconductor crystal, depending on which impurity has been added to that region, is called an N-type or the P-type. And of course this is then used in creating or making basically, for example, NPN transistors or PNP transistors and so on and so forth. So the whole thing is basically connected together. So basically, you know that normally basically in electricity, the electrons are the negative charge carriers. Electrons are the negative charge carriers, which are used to conduct charge in a conventional conductor. Now, semiconductors contain basically something called positive charge carriers. Semiconductors contain something called positive charge carriers. Positive charge carriers, which are technically called holes. And what this hole is that basically basically the way that they talk about it in physics, they say that they illustrate this by basically, well, just using the very concept of a hole, and the hole is something that can be filled with an electron, something like that, and then the hole can basically move all across the semiconductor, and so that way it is doing its job of, which is basically operating as a charge carrier. So that's something like that. But of course, in order to understand that and understand exactly how that works, of course, you need to go back and read the physics and electronics related to this, which is not the topic of this discussion here in this book. Now the impurities added to an N-type region increases the number of electrons capable of conducting charge, whereas the impurities added to a P-type region increases the number of holes capable of conducting charge. So this is important. Okay, so now the next thing that we have here is that it says that when a semiconductor chip contains an N-doped region adjacent to a P-doped region, a diode junction, often called a PN junction, is formed. Diode junctions can also be made with either silicon or germanium. However, silicon and germanium are never mixed when making PN junctions. So what these chips are, basically you have your chip over here. Suppose that this is a chip, and I'll show you what the chip is. And you have some region over here, some region over here. Suppose that this is an N-doped region. You have an N-doped region over here, and you have a P-doped region over here. So the N-doped region is basically the region where there is basically electrons as the charge carriers. The P-doped region is the region where there is the holes as the charge carrier, and then they will be basically kind of put together in adjacent regions, and that becomes a diode junction or a PN junction. And what a chip is basically this thing over here that you can see. So you see this chip, the chip comes from sand to silicon. So let's watch this video together. Okay, so as you can see, for example, this thing over here, this CPU, of course, contains probably millions and millions of transistors and diodes inside it, even resistors and capacitors. But then you can imagine that on that wafer-like thing, all of these things are basically placed, and the whole thing is basically called a chip. And so that's basically, for example, a very, very, very tiny part of that is just a diode or a transistor, and there is usually basically different layers of different things on top of one another in a CPU like that. So so the diagram of a diode basically is, now to wrap this up, let's go through a couple of things here. So a diagram for a diode is usually this way. So you have basically a P region over here and an N region over here, and then these are the leads of your diode. So this is the diagram of a diode. Or you could do it this way. You could also basically do it this way, N and P. That is also the diagram of diode. Now the P material in a diode, the P material is called the anode. This is important. This is important in then basically later on when we want to talk about transistors, because a transistor is nothing but basically two diodes put together in one package, kind of like something like two diodes put together in one package. So the P-type material is called the anode, and the N-type material is called the cathode. So this is also important to understand. So the N-type material, which is basically the electrons as the charge carriers, is called the cathode, and the P-type material is called the anode. Now, of course, in order to understand why this is so, you do again need to understand the physics behind this, which is beyond the scope of our discussion here. So so this is again important. And so since in a diode, if you basically draw the diagram like this, if this is the N-type material, this is the P-type material, the anode and the cathode, so then if you were to draw the schematic of this diode, it would look something like this. So this would be your cathode, and this would be your anode, right? And the direction of current flow in a diode is basically based on the conventional, of course. Current flow is basically in this direction, meaning that current flows from the anode to the cathode, meaning from P to N. And of course you know that if you want to forward bias your diode, you have to, if your diode is basically in this orientation, then you connect this to the negative pole of the battery, and then positive pole of the battery is connected here, meaning that your anode is connected to the positive. And in an electric circuit, you know that current goes in this direction, from positive to negative. So what that means is that the current comes this way and then this way, and then it goes from anode to cathode. The anode is the P-type material. The cathode is the N-type material. So that's again something to note here. Of course, even in the practical part of this chapter, all of this theory is not that important. But when we talk about transistors, excuse me. Okay, so I was interrupted by someone, and so basically that is the whole story there. So this is the p-type material anode, the n-type material cathode, and so on and so forth. This becomes important when we talk about transistors. We will talk about that later if it's necessary, of course. So now what we need to do is, the next video we will talk a little bit about basically forward bias diodes, and let's actually do this over here. Now one important thing here is that, as you can see in the schematic of a diode, basically this is like an arrowhead. As you can see here, this part is like an arrowhead, and it basically points in the direction of basically current flow. The current goes from anode to cathode in the conventional current flow, of course. And so, for example, if you have this circuit over here, suppose that you have a power supply over here, you have some resistor over here and some diode over here, and the cathode is connected to the negative pole of the power supply. The anode is connected to the positive pole of the power supply, and the diode is connected is basically in this orientation, is connected correctly to permit current to flow, meaning that the diode is basically forward biased. It's basically forward biased, meaning that it conducts, or in other words you can say it permits current to flow. Okay, and basically technically we say that the anode which is connected to the positive pole of the power supply, and the cathode which is connected to the negative pole of the power supply, the anode is at a higher voltage than the cathode. We say that the anode is at a higher voltage than the cathode. Okay. So this is called forward bias. Now, in a forward bias diode, the anode connects to a higher voltage than the cathode, and the current flows. So in a forward bias diode, which is basically something like this, the anode connects to a higher voltage than the cathode, and the current flows. And if you had some circuit like this, for example, if you have some circuit like this, like the one over here, suppose that you have a resistor over here, you have some diode over here, and this diode is connected here, and if this is positive negative, you see that cathode is connected to the positive pole of your power supply. The anode is connected to the negative pole of your power supply, and of course in this orientation your diode is not forward biased. Which is called, basically technically we say that it's basically reverse biased. And in this orientation, the current is not flowing. Current is not flowing. Current is not flowing. Meaning that technically you can say that the cathode is connected to a higher voltage than the anode, basically. And basically it's called reverse bias, as we mentioned here. Now, there is something called the concept of a basically a perfect diode. That is also something that you need to be familiar with. A perfect diode. So basically a perfect diode is the kind of diode where there is no voltage drop across the junctions of the diode when it's connected to the power supply in a forward biased mode. What that means is that suppose that you have this circuit over here, and this is positive, goes to some power supply connected to anode, and then the cathode goes to negative. So in this configuration, of course, your diode is conducting. Your diode is conducting. Your diode is conducting, and it is forward biased. It is forward biased and conducting. Now what happens here is that basically if you had some circuit, for example, something like this in here, for example, two resistors, let's say R1 and R2, and if this was V of S, then as we saw in the previous chapter, we had some voltage drop over here and some voltage drop over here. This was, for example, V1, some voltage drop over here, and we had some V2, some voltage drop over here. And in this series circuit, we saw that V of S was equal to V1 plus V2. The voltage drop across R1 plus the voltage drop across R2 was equal to the power supply voltage. Now this is also something like this circuit, meaning that the diode and the resistor here are basically connected in series. So now the point here is that if your diode was a perfect diode, of course there would be no voltage drop across the p-n junction of the diode. But of course no diode is a perfect diode, and there is always some voltage drop across the p-n junction of the diode, meaning that if there was no voltage drop across the p-n junction of the diode, then of course your whole power supply voltage V of S was available on this diode would drop over here on this resistor. But that's not the case, meaning that what happens practically is that there is some voltage drop across the p-n junction of this diode over here, and this is basically, you can call V of D. You can call it V of D. You can call this V of D, and then if I call this R, then you can call this V of R. Now what happens is that again in this circuit, V of R plus V of D is equal to V of S, of course. Now in these types of circuits where you have a forward biased diode, meaning the anode connected to positive, the cathode connected to negative, V of D is always equal to, or you can actually assume that the voltage drop across the diode is 0.7 volts. V of D is always 0.7 volts. That is for a silicon diode. That is for a silicon diode. If you had a germanium diode, then V of D would be equal to around 0.3 volts. That is for germanium diode. That is for the germanium diode. And of course, when you practically breadboard this circuit, or actually have some physical power supply, some diode and some resistor connected together, if you measure this voltage, it's somewhere around 0.55, 0.6, 0.7. It depending on the diode, that of course the voltage drop changes, but it's always somewhere around 0.7. And that's basically why in calculation we always take this value to be 0.7 volts. And of course then the rest of the voltage is dropped across this resistor over here. Now in basically, suppose that you have a circuit. Suppose that now you have a circuit, for example, your V of S is equal to 5 volts. And then, for example, if you had a diode in your circuit, V of D would be so somewhere around 0.7 volts. Now, since your power supply voltage is 5 volts and your V of D is 0.7 volts, this is around 20%. 0.7 volts is almost 20% of 5 volts. So it's 20% is a large percentage of your power supply voltage. And then around 80% of the power supply voltage would drop across the resistor over here. So in cases where basically the power supply voltage is low, like 5 volts, 3 volts, or something like that, below 10 volts, we take this voltage drop across the diode, we take that into consideration, because it's important, because it's a large percentage of the power supply voltage. But suppose that in the same circuit your V of S was, for example, 25 volts. Now when you have 25 volts there, if your V of D is equal to 0.7 volts, then in that case it's not really that important, meaning that it would be like 1/25 of, that would be 1/25 of basically that voltage, which is somewhere around 1/25 is about basically 4%. Is about 4% of basically about 3 or 4% of the power supply voltage, and 3% or 4% doesn't really matter that much. So what that means is that in circuits where your V of S is above, where V of S is greater than 10 volts or so, then in those cases, then you don't take that voltage drop across your diode into consideration. Otherwise, if your voltage is below 10 volts, then you basically you take care of that. You take care of the voltage drop in your calculation as well. And again, for a germanium diode, we take this value to be 0.3 volts. For a silicon diode, it's 0.7 volts. And of course, again, a perfect diode is the kind of diode that if you had it in this configuration of forward bias, there would be, and if the circuit was running, there would be 0 volts voltage drop across the PN junction of your diode. meaning that in forward bias your diode would behave like a switch, like an electrical switch, meaning that you would have your power supply over here, your resistor over here, then you would have a switch over here, and then back to basically power supply. So here you have your R, and here you have your switch closed, and it's conducting. An electrical switch closed has zero voltage drop across its leads or across its terminals, because the resistance between the two terminals is zero, right? When the resistance is zero, when you have V is equal to IR, suppose that R is equal to 0, V becomes 0. So since in a switch your resistance is 0, then the voltage drop across the switch becomes 0, and that's basically that would be basically a perfect diode conducting. But now the diode is supposed to be it's supposed to be conducting, but since it's not perfect, then there is this voltage drop across the junction of the diode, and that means that there is some resistance over here, which results in this kind of voltage drop across the leads of the diode, right? And that's basically it. So what that means is that a forward biased diode in this orientation just acts as a switch, as a closed switch, meaning that you have this switch over here and it goes to your power supply, and this switch is closed. Here is your R, here is V of S, and your switch is closed, and so the diode is conducting here. So it acts as a closed switch, except that there is 0.7 volts voltage drop across these two terminals, and which doesn't really happen in the case of an actual switch. And a reverse bias diode, which is to say basically a diode which is in this orientation, meaning that the cathode connected to positive, anode connected to negative, which is a reverse bias diode, it acts as an open switch, meaning that it's not conducting, there is no current going through the circuit. So that's basically what you need to know about reverse biased and forward biased diodes. Now what we have in the next video is basically a project that shows us a little bit about diodes. We will work with a simple diode and a resistor. We will measure a couple of things, a graph and something like that. So I will see you in the next video.